Welcome back. In the next part of this lecture, we'll be talking about some applications of quadratic functions. And one nice one would be things involving revenue, cost, and profit. Because if we have a revenue function or a profit function that's a parabola, then we know that it will either have a maximum value or a minimum value. So we'll be able to find maximum and minimum values for profit or cost or revenue just by finding the vertex of our parabola. So just some things about revenue, profit, cost in general. In these sorts of scenarios, I'm going to be having X represent the number of items that we produce and sell. We're going to assume that whatever I produce, I sell, that there's nothing going to be left over or unsold. And as it is generally in real life, there's a relationship between the price that you're going to sell things at and how many things you sell. And that relationship is called a demand equation. A demand equation is an equation that will give the relationship between X, number of items that you sell, and P, the price you're choosing to sell those items for. So once we have our number of items that we're interested in selling, X, and the price that we're planning to sell them for, P dollars, then your revenue, the amount of money that you take in, is just however many things you sell, X, times whatever price you're selling them at, times P. And so we can come up with a revenue equation. And if we're lucky, the revenue equation will be a parabola, in which case we can find when the revenue is maximized or minimized. If you happen to have a cost involved, so of course that's not a surprise, most things are not free, so you might have some items that you're producing, but it costs you a certain amount of money to make them. So you might have an equation that tells you for X items, here's how much it costs to produce them. And so if you wanted to know the profit, profit is just the difference between how much money you earn or take in minus how much money you spend, revenue minus cost. So here we go. We've got an example. We've got a demand equation given to us. When the price of an object is P dollars, then we're going to sell X objects. And that relationship is given by this equation, that you could say that X, the number of objects you sell, is 40 minus 1/5 times P. Or you could rewrite it by trying to rewrite this equation and solve for P. If I multiply everybody by 5, and then solve for P, so we have two equivalent ways of expressing this relationship between the number of items we sell and the price that we're going to sell them at. Either you could say X, the number of items you sell, is 40 minus 1/5 P, or you could say P, the price that you're selling them at, is 200 minus 5X. The one thing I'm going to mention here before we move on and actually answer things in part A and B is to notice that for this demand equation, that this is a linear relationship, this is a straight line relationship, and the slope for this line happens to be negative. It's a decreasing relationship. That's telling you that if you were to increase your numbers of things that you sell, then the price will have to decrease. In other words, the lower your price is, the more things you'll sell, or the more things you want to sell, the more you'll have to lower your price. And of course, the reverse is also true, that if you decrease the number of items you sell, then that means you can increase the price that you sell them at. Or the reverse is true, that if you increase the price that you're selling these things for, the less of those items you're going to sell. Okay, so let's continue on here. We have our first part, which is find our revenue equation. And we know that our revenue equation, R of X, is just our price times the number of things that we sell. Now, of course, we want to have our revenue just as a function of X. We don't want it to be a function of two variables. But conveniently enough, we happen to already have P, our price, expressed in terms of X. So instead of having it as P times X, I can rewrite this as 200 minus 5X times X. Which, if I were to expand that out, that's negative 5X squared plus 200X. There we go. So there's our revenue equation. A couple of things just to notice about this before we go on. One thing that I'm going to mention here is notice that my revenue equation, I have it already in factored form, which means that if I want to find X intercepts for this revenue equation, then it's really easy to do because it's already been factored. So just mentioning that now because that's a little bit of foreshadowing for when we get to part C. But for part B, the question is, how do we know that it has a maximum revenue and not a minimum revenue? The answer is because the coefficient of the x squared term is negative 5, then the parabola opens downward and must have a maximum value, not a minimum one. And that's, again, just thinking about the shape of our graph. If we know that something is a parabola opening downward, then wherever that vertex is, that would be where the maximum value is, not the minimum value. You would only be able to have a minimum value if you had a parabola that was opening upward, but that would only be possible if the coefficient for the x squared term was a positive number, which it's not. So since our coefficient for the x squared term happens to be a negative number, then we know our parabola opens down, and if our parabola opens down, well then good for us. That means we must have a maximum value, not a minimum value. Okay, so next, part C. Part C is, if we wish to maximize our revenue, how many objects should we sell and for what price? Or in other words, we need to find the vertex. That's what we need to do in order to find our maximum value and also where the maximum occurs. That's what we need to do for part C. And this is where the hint that I'd mentioned will come back. Because remember, to find a vertex, you can do one of a couple of things. You could try to complete the square. That would be one way that you could try to find the vertex, but I don't know if that's really the easiest way to do things here. The other way to find the vertex would be to find the x intercepts, and once you have x intercepts, then the vertex would be at the x coordinate that's right in the middle of the two. And so that's how I'm going to tackle this. I already have r of x factored. So if I wanted to find x intercepts for r of x, I would let r of x be equal to 0. That means I would have 200 minus 5x times x equal to 0. And then that would give me two solutions. Either x is equal to 40, or x is equal to 0. So you would have two x intercepts, one at 0, 0, and the other one at 40, 0. And once you know that, then you know exactly where the axis of symmetry is. The axis of symmetry should be exactly between the 2 points. So x is 0 plus 40 over 2, or 20. So your axis of symmetry is through the line x equals 20. And so you know your vertex should also be where x is equal to 20. And your y value for your vertex should just be the value you get by putting 20 in for x. And so if you went back and put in 20 into r of x, you would have, after you simplify it, that it cleans up to give you 2,000. So if I were to go back and put 20 into either version, either into this version of R of X or into this version of R of X. Both of them give me a revenue of 2,000. So now I can answer my question here. The question is, how many objects should I sell and for what price? And what is our revenue? So I'll answer the first couple of things. So to maximize revenue, we need to sell 20 items. This earns us a revenue of $2,000. That's the first part. The other part of the question was, what was our price? And for that, we need to go back and remind ourselves that we have a relationship between price and numbers of items we sold. We know that the number of items that we're going to sell is 20. And so if you go back, you have a relationship here that tells you if you know the value of X, you can use this to find out what your price should be. So your price should just be 200 minus 5 times X. So our price should be 200 minus 5 times our value of X, which turns out to be 100. So that means that we should set our price at $100 to maximize revenue. So that means if we want to maximize our revenue, we just need to set our price at $100 per item. That means we will sell 20 items, and that means we will earn a maximum revenue of $2,000. Okay, so now we've got a cost function being thrown into the mix. I'm describing here in words how I created this cost function. I have fixed costs of $640, so I will have to pay $640 for my costs, no matter if I sell anything or not. And then for every item I produce, for every X, I'll have to spend an extra $20. That's where this cost equation is coming from, saying that my cost would be $640 plus $20 times every item that I make, 640 plus 20x. And so for our profit function is just our revenue function minus our cost function. And we've got both of those. We know that our revenue function was minus 5x squared plus 200x. And from that, we're going to subtract our cost function, 640 plus 20x. And just to simplify that, we'll have minus 5x squared plus 180x minus 640. So there we go. We've got our profit function, and the thing to note here, and this is our answer for part E, that since our profit function is a parabola whose leading coefficient is negative, then this means again that we are a parabola that's opening downward, which means yet again that this is something that has a maximum value, not a minimum value. So we'll say here that since the coefficient of the x squared term is negative, then the graph of p of x opens downward, so it has a maximum and not a minimum. If the coefficient for the x squared term had been positive, then this would mean that we would be opening upwards. We would have a minimum, not a maximum. But r of x does have a leading coefficient that's negative, so we are opening downward, which means we do have a maximum. And now, again, we want to find the question of the vertex. We want to maximize our profit, so we, again, are going to need to find our vertex. We want to know what our maximum profit is, how many things we should sell, and for what price. And for this, you can again do this a variety of different ways. This one is maybe not as easy to find X intercepts. So this is one where maybe I'll do completing the square just for fun. So I will take my profit equation, and from the first two terms, the negative 5x squared and the 180x, I'll factor out the negative 5. And I'll leave the 640 over by its lonesome here outside the brackets. And so next thing that we would do is take that coefficient in front of the x term, that negative 36, we would cut it in half to be negative 18, and then we would square it. Negative 18, when you square it, that's 324. And then for the next step, I'm going to have this negative 324 leave the brackets, and when it does, it'll need to be multiplied by that negative 5 that's in front of the bracket. So I will rewrite this and say, well, actually what I have, I will leave the x squared, the 36x, and the 324 inside the brackets. The negative 324 leaves the bracket, and it's multiplied by negative 5 to give me positive 1620. And then the last thing for me to do is just to clean things up. Those three terms that I have, x squared minus 36x plus 324, is the same thing as x with half of this coefficient, so x minus 18 squared. And then the last two terms, the 1620 minus 640, that adds up to 980. So that means that you've got your vertex at 18,980. So there we go. We know where the vertex is, and now all we need to do is make our conclusions and talk about what do we get as our result from all of this. What does all of this mean? So first off, I can say, remember that X is the number of items that we sell. So to maximize profit, we sell 18 items, and the maximum profit is $980. Remember that the profit function has the input as number of items and the output as the profit. So we know now how many items we should sell, 18. We know what our profit is. The one thing we still need to find is this, which is what is the price that we're selling every item for. But same thing that we did before, where we're going to again use that demand equation. We had the relationship between price and number of items sold. Price was 200 minus 5 times X. So for our price, should be 200 minus 5 times X. And then the only thing that we need to do after that is just to calculate what our price is. And then once we know that, we'll have our price that we need to sell everything at, which is $110. So that means that if we want to maximize our profit, sell each item for $110. And just to check here, you're selling selling 18 items for $110. You can go back and double check to see that if you're looking at your revenue equation and your cost equation, that together selling your numbers of 18 items at $110 each would give you a profit of $980. Again, if you are thinking about what we've done so far, This is really just an exercise in finding the vertex for a parabola. For both of these, for the revenue equation as well as for the profit equation, they were both parabolas, and so because of that, we knew that they would have to have either a max or a min, depending on whether they opened up or down. And once we concluded that both of them were opening downward, then we knew that both of those functions had maximum values. Another example here, we've got a farmer who's got 3,000 meters of fencing material. So that means that all of these sides around the outside, plus the little fencing that's in between, all of that together would have to add up to 3,000 meters. And we're trying to make three little side-by-side areas that are all equal in size. So I'm just going to start by labeling some things with variables, and then I'm going to define them in words afterwards, just so that I'm pretty clear as to what I mean. So here I'm going to make three identical shapes, so that means that the width of each of these three, I'm having them all be identical. They're all x's, and they all have the same length. This distance, they're all y for each of my three enclosures. So I'm going to define the x as the width of my enclosures and y as the length of my little enclosures. And also I have to be kind of clear here, because when I say width and length, length is not always the longer side and width is not always the shorter side. So I want to make it clear that the y side, those are the sides that are being shared. So that's why I say there where the lengths are the common sides for the three enclosures. So y are the sides that the enclosures have that they're sharing. And so we know something already, which is that we're using 3,000 meters of fencing material. So that means that x, 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 and another x, and another x, and another x, and a y, and a y, and a y, and a y, that all of those sides together should add up to 3,000. So one thing that we know is that 6x plus 4y, that should add up to 3,000. The second thing here is, now this is getting to the question itself, we want to know what is the maximum area for each of these three enclosures. So I guess what we'll need is an area function for each enclosure. For each of these three enclosures, the area is just length times width. It's just x times y. We have to be kind of careful here, and this is where we need to be careful reading the question itself. What are we trying to maximize? Am I maximizing the area of each enclosure, in which case the area is x times y? Am I maximizing the area of the entire shape, in which case the area would be 3x times y? So I have to be a little bit careful here. Now, I've got that my area is x times y, and that's something involving two variables, not one. I'd like this to be an equation involving only one variable. So what I'll do is I'm going to take this first equation that I have and rewrite it. I'm going to solve for one of my variables, and it doesn't really matter which one you want to solve for. You could either solve for y or solve for x. I'm going to solve for y here. Divide everybody by 4. 6 divided by 4 is 6/4, or same thing as 3/2. And now I can take what I have here and use that to replace the y that's in equation 2. So we're going to look at equation 2 again, and now replace the y with what y is equal to, 750 minus 3 halves x. Which, if you were to expand that out, that would be negative 3 halves x squared plus 750x. And I'm mentioning that now just so I can confirm before I move to the next page that this is the equation of a parabola that is opening downward. And I know that it's opening downward because the coefficient for the x squared is negative. And if it's opening downward, then that means we do have a maximum and not a minimum. Okay, so now we just need to think about what to do. And we want to maximize this, which means we need to find the vertex. And you've got, again, two options as to what you might consider doing. You might try to complete the square, which I don't think that that's the nicest and easiest way. Or you could find X intercepts and then find the vertex as being in the middle. And actually, this seems to be the easiest way, because if we're looking at our area equation, we can see that we already have it factored, which means finding x-intercepts will be actually quite easy to do. So let's do that now. Let's find our x-intercepts. So for x-intercepts, we're letting our area function be equal to 0. And then we just have to say, well, okay, either x is 0 or 750 minus 3 halves x is 0. And for that second one, if you were to solve that for x, so multiplying both sides of the equation by negative 2/3, you'd come up with a value for x of 500. So that means you have x-intercepts at 0, 0, and also at 500, 0. And so you know then that the axis of symmetry should be right in the middle between the x value of 0 and the x value of 500. So our axis of symmetry is the line x equals 250. And wherever the axis of symmetry is, that's the x-coordinate for the vertex. So you can say that the vertex is at x equals to 250. And once you know what the value of the x is for the vertex, you can go back to your area equation that you have and put in the 250, and we'll be able to find out what is our area. So if we do that, so our area would be 250 times 750 minus 3 halves times 250, which if we run that through our calculator, we get 93,750. So that answers part of our question. Our question was, what is the maximum area for each of these three enclosures? And we now know that. We now found the maximum area. That happens to be 93,750 square meters. The other thing that we need are the dimensions of each enclosure, and for that we need the x value and the y value, the lengths and the widths. So we already know what the value of x is. To find the value for y, we have a relationship between x and y, so we'll use that to find out what y needs to be. So we'll say y is 750 minus 3 halves times whatever x is, which if you run that through your calculator, you'll find the y value is 375. So just to summarize, each enclosure should have a width of 250 meters and a length of 375 meters. This will give a maximum area for each enclosure, of 93,750 square meters. And there we go. We've solved our problem. The original problem was, what are the dimensions of each enclosure? So each one should be 250 by 375. So that means that 250, 250, 250, we'd have 750 meters in this direction and 375 in this direction, and that would make each of these 93,750 square meters. So you'd have 93,000 plus another 93,000 plus another 93,000. You'd have just shy of 300,000 square meters for your total area for all three enclosures. Our last one that we want to do here is this rocket example. I've got a rocket launched into the air, and I've got its height in meters above sea level after t seconds given by this equation. And for me, I want to find the maximum height the rocket attains. In other words, I want to find out what is the y value for our vertex. Before I do any of that, I know that this is a parabola that is opening downward because its leading coefficient is negative. So wherever the vertex is, that will be where we do have a maximum value. And this is one where, if you're thinking about the sorts of questions that it's asking, it only wants to know what the maximum height is. In other words, we only really need to know what where the vertex is. And if we're thinking about this one, the numbers do not look very nice at all. If you're thinking about trying to find the X Intercepts, those you're not going to be able to find them by factoring. You're going to use the quadratic formula, and they're not going to be nice numbers. If you're thinking about completing the square, that certainly is not going to turn out to be nice with these numbers. We've got decimals running around here, so it feels like a bad choice. So this is the one place where I would use my formula for the vertex. Remember that I said that for the vertex, you could find it at the point negative b over 2a and the y value at negative b over 2a. That would be the formula that we gave for our vertex when our polynomial is just written in that standard form of, in this case, t squared and t and constant. Here the a, the b are just, again, the a is the coefficient of the t squared term, negative 4.9. The b is positive 229. So for our vertex, the x coordinate, x should be negative 229 over 2 times negative 4.9. That's negative of b over 2 times a, which when you run that through your calculator, that gives you about 23.367. So after about 23-ish seconds, the rocket gets its maximum height. And so the height then, after 23.367 seconds, again, just finding that by putting that in for t, and we come up with a value for height that's about 2,909.561. So if I were to just summarize this in words here down below, I would say after 23.367 seconds, the rocket achieves its maximum height of 2,909.561 meters above sea level. And then there we go. So this formula business here of finding the vertex through the formula, it's a nice option, but I only tend to use that for ones where factoring or completing the square either are not easy to do or the numbers are not very nice. And also, especially if all I'm looking for is just a quick numerical answer. If this were something where maybe I wanted to also find other information about this parabola, then maybe I might want to find intercepts or maybe complete the square. But for this, all I'm looking for is the location of that vertex, and so why not take the easy way out and use the formula? So that's what I've done here.